Okay, so as I mentioned last time, I posted up on Canvas a recording for chapter one. So we're not going to officially go over chapter one. There's not much in there really to talk about. I think it's only like 12 minutes to recording, so make sure you do watch it. You're responsible for whatever's in there. I think it's basically just a sort of scientific method and that type of stuff. So, like I said, nothing super long to worry about. We're going to get into today chapter two, which is measurements. And um, let's get sort of started on it. So, measurements, and one of the important things about measurements is the units. And units are really important, especially in chemistry. Whenever you make any type of measurement, you should always include the units. So, for example, if I wrote 500 up here, you know, what am I really talking about? And when we look at 500, you really have no idea. That could be $500, which would be great. It could be 500 pennies, still great. It could be 500 apples, 500 cars, whatever it may be. A number by itself really has sort of no meaning. It has no sort of understanding of what it is, especially when you're taking measurements if you don't include the units. So you should always include the units. Maybe these are grams or something like that. So 100% of the time, if you're taking any type of measurement, there definitely should be a number, and there also should be units associated with it to let people know exactly sort of what the number means, what we're sort of referring to. Um, you should also, as we'll talk about when you do calculations, you also should include units in your calculations as well. Again, for your sake, so you can see if things cancel out correctly. And again, it gives people a frame of reference of what that number really does mean. Now, units, as I mentioned, is the part of the measurement that really tells us sort of the scale of what we're dealing with. When we talk about units, there's two widely used sort of systems of units. One is sometimes referred to as the English sort of system. That is the system that we use here in the US mostly. And really, pretty much everybody else uses pretty much the metric system as the other sort of version of the units. So as the world sort of interacted with each other, obviously it can be not a great thing if sort of one place is using sort of English units, one's using metric units. It can cause sort of problems. So in 1960, they sort of got together and had a conference on sort of units and weights and measures. And they came up with sort of a standardized system of units that's oftentimes used in chemistry, for example, and the sciences. And that is what is referred to as the SI system of units. The SI system of units basically stands for the International System of Units. For the most part, that is going to be the metric system. Thank you. Did everybody sign? If not, head back that way behind you. Thanks. It's pretty much based off the metric system. So you'll see a lot in here, the SI unit for mass is this, or the SI unit for some other unit is something else. So let's take a look at what some of the fundamental SI units are. For mass, it's a kilogram is sort of the standard SI unit. For length, it is a meter. For time, it is the unit of seconds. For temperatures, maybe a temperature you haven't used a lot, but in chemistry we use this unit of temperature pretty much for everything. Almost every time that you have some type of temperature value, especially a temperature value that you need to put into like a formula or something like that, Kelvin is really the temperature unit that we use for the most part. So you'll see Kelvin a lot. There are other things. We sometimes will see moles, which are abbreviated MOL. That's sort of the amount of molecules or matter really that is present. But these are the standard sort of guys for mass, length, time, and temperature that we come across. We do use prefixes, as we'll talk about here shortly, to sort of change the meaning of some of these values. But these are their standard sort of abbreviations. And that table is from your book as well. You should have one. So let's talk a little about some of the common measurements our units that we're coming across for length, volume, and mass. So starting for length, the SI unit there is a meter. 1 meter is 39.37 inches. Very common sort of conversions. For example, there are, for example, 100 centimeters in 1 meter. So that is definitely a conversion that you should know, and it's used a lot. I would say also this one down here, 1,000 meters is a kilometer, is also a very common sort of length conversion. Again, a reminder here at this school, they want you to know all these sort of things, so make sure that you sort of make a list and kind of put them to the side there. 1 centimeter is equal to 0.01 meters. 1 decimeter is zero point 0.1 meters. There are, in terms of millimeters and centimeters, right? There's 10 millimeters in a centimeter, right? If you look at it like a ruler or something like that. So I'd say these two for sure are definitely some conversions that you should come across. These two numbers are basically the same number, and we'll talk about this a little bit later on in this chapter, but this is scientific notation. The way this is written, 1 times 10 to the minus 2 is scientific notation. And obviously 1 times 10 to the 3 is scientific notation there for 1,000. We'll talk about that a little bit later on here in this chapter. As I mentioned before, very commonly we do use prefixes to change the meaning of some of these values. And we'll just go with, you should know this probably, this table. And we do come across, I would say, in this class, and as you continue on in other classes, you'll come across most everybody that's on this list. But definitely for us, we definitely will hit a lot of times kilo, centi, milli. We don't come too much in nano and micro, but as you go to like 1A, for example, you will hit those guys as well, and mega, for example, as well. So this is just a good table to know. This is the prefixes that are used for a lot of units and measurements. This is the meaning in sort of a number form, but a lot of times people use this table and kind of use it in this form, and this is the scientific notation form. And let's talk a little bit about this, and we'll talk about it again, because oftentimes when people do these or use these type of prefixes, for example, as like conversions or something like that, they oftentimes will sort of mess them up. So when you go to this table, or when you kind of know this table, and especially we'll look at this column here, these are all basically in scientific notation where it says 10 to the 6. That is basically 1 times 10 to the 6 in terms of scientific notation. But how this works is this. Let's just take, for example, let's take centi here. And when we look at centi, it says 10 to the minus 2, which again is basically 1 times 10 to the minus 2. And what that means is in one of the prefix units, that's how much there is in the base unit. So when we talk about prefix units to base units, this, for example, if we were looking between centimeters and meters, in this case, meters is the base unit, right? This is sort of the prefix unit. And when we look at this, the proper way to use this is in 1 centimeter, there is 10 to the minus 2 meters. And it's very common that people will do that backwards. They'll go like 10 to the minus 2 centimeters in 1 meter and obviously did the calculation wrong. So that is how you should read this list. By the way, it does not matter the actual base unit. If I was doing centigrams to grams, 1 centigram, 10 to the minus 2 grams. If I was doing centiliters to liters, 1 centiliter would be 10 to the minus 2 liters. So it really doesn't matter what the base unit is. The prefix the same when you attach it, but it is one of the prefix units basically equals what you have in this particular column here. So if we were doing kilo, which is 10 to the 3, in 1 kilogram, which is our prefix unit, that would equal 10 to the 3 grams. So again, that is the proper way to sort of use those values that are on there. Now, you could get sort of the larger values, if you will, sort of in this column, or not really in this column, but you can use sort of the larger conversions. For example, if I take my 1 centimeter is equal to 1 times 10 to the minus 2 meters, and I divide each side by 10 to the minus 2, or 1 times 10 to the minus 2, that will give me my 1 meter is equal to 100 centimeters, which is again the same conversion that we saw on the previous slide. So that is how you could kind of get, if you want to remember the bigger sort of number or regular sort of number, you could just divide the scientific notation to the other side, take 1 divided by it, and that'll give you sort of the bigger conversion, and that'll be the opposite way of using it. So some people like to use the sort of numbers and not the scientific notation when they're using the prefixes, which is fine. But again, a lot of times you'll kind of see it in this form, and that's a good way of doing it. So once again, if I had, for example, here, nano, which is 10 to the minus 9, and that would mean in 1, for example, nanometer, which is our prefix unit, there would be 10 to the minus 9 meters. Any questions on how to use that there? Like I said, we definitely will come across these prefixes throughout the semester and as you continue on. So like I said, this table is probably a good one to sort of know all those prefixes. The ones I put dots next to, probably the ones we'll see most of the time, which is almost everybody there. We probably won't see too much of the micro or nano, but definitely as you go to 1A, you definitely, like I said, you will kind of see those guys. This is a ruler, and sort of the difference between the English system and the metric system. This is an inch, which typically we measure things in, and that equals 2.54 centimeters. We'll see it a little bit later, but that is a conversion they definitely want you to know as well. 1 inch is 2.54 centimeters exactly. So make sure you know that. By the way, when we look at this, right, this is inches on top. These are centimeters. What are the small guys here? Yeah, those are millimeters, right? And there's 10 millimeters in a centimeter, right? So again, that's what those little guys are on the bottom there. Bless you. When we talk about volume, that is the amount of three-dimensional space that is occupied by a substance. The sort of SI unit for volume is meters cubed. Some very common sort of volume conversions are cubic centimeters and cubic decimeters. Some common ones definitely that you should know, 1,000 milliliters is 1 liter. We definitely use that a lot. So a lot of formulas will require the volume to be in liters. And a lot of times when we take measurements of volume, oftentimes it's in milliliters. So going from milliliters to liters is a very common conversion. And also going in the opposite direction as well, going from liters back to milliliters, also a very common kind of conversion. 1 milliliter is equal to 1 cubic centimeter. That is also a common sort of conversion. Now you may be saying, isn't centimeters a unit of length? And centimeters is a unit of length. But if you have something, for example, like a cube or something like that, and you take 3 length measurements, the length times the width times the height, and if you take each of those measurements, say in centimeters, you'll have centimeters times centimeters times centimeters, which will actually give you a cubic centimeter. That is a volume. Each of these individual sort of measurements are length measurements. So if you take those 3 sort of measurements and multiply them together, you will get basically a volume. And that's why we have something like decimeters cubed, meters cubed. Those are all, again, basically volumes achieved that way. So when you see a cubic centimeter, we are referring to a volume. If you see just a centimeter by itself, it is a length measurement. That is also something that's really important as well, is the understanding of what those units represent. So you want to know that when you say this is a cubic centimeter or this is a milliliter, that you're talking about a volume. You want to know, obviously, if you're talking about centimeters, meters, something like that, you're talking about a length. Any questions on that there? Now, mass is the quantity of matter that's present in an object. Matter basically is anything that can occupy space and has mass. The SI unit there for mass is a kilogram. Again, some very common sort of mass conversions that we use a lot. There are 1,000 grams is a kilogram. So again, that is a very common conversion. By the way, again, that is the same as we saw previously. 1 kilogram is 10 to the 3 grams. So 10 to the 3 is basically 1,000 because that is 1 times 10 to the 3 in scientific notation, which basically equals 8,000. So it is the same sort of conversion. Also, milligrams to grams is a common conversion. So there's 1,000 milligrams in a gram. And again, that would be the same as sort of using the milli conversion that we saw previously. This is a balance, which is basically used to measure mass. It's basically like a scale, if you will. And you put, obviously, your whatever you want to get the mass of on it, and it will give you, obviously, the mass measurement. Now, there is a difference between when we talk about mass and we talk about weight. And the difference between mass and weight is mass is independent of the force of gravity, and weight does take into account the force of gravity. So when we measure something on a balance, for example, we do refer to it as the mass of the object and not the weight of the object, as the balance is set to take out the force of gravity sort of as you measure it on there. But for example, if you measured your weight here versus your weight on the moon, it would be different because obviously the gravity is different in both places. But in chemistry here, we do refer to weighing things as the mass. And again, it's confusing because the process we do is weighing basically, right? So by doing that, that is telling people maybe you should call it the weight, but it is referred to as the mass, as these things are basically taking the gravity out of the calculation. Let's talk a little about temperature and the 3 different types of temperature scales that we will come across here and sort of the conversion between them. So the 3 sort of types of temperature scales is degrees Fahrenheit, degrees Celsius, and Kelvin. And again, one of the major differences you can kind of maybe see from that is we actually do not use the degree symbol with Kelvin. So it's like just like 273 Kelvin is the way it's referred to. But we do use, degrees Celsius or degrees Fahrenheit. The Fahrenheit scale, water boils at 212 degrees Fahrenheit, and 32 degrees Fahrenheit is where it freezes. That is the normal, what is sometimes referred to as the boiling point and freezing point, right? Temperatures. This is the scale we commonly use here in the US for like our temperature and stuff like that, 98.6 degrees Fahrenheit, or like it seems like today, 120 degrees out there. It's going to be later on today. Celsius is the metric system. On the metric system, water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. That is something you should know in chemistry here. The 100 degrees Celsius is the boiling point for water, and 0 degrees Celsius is the freezing point for water. Those are, again, common numbers that we do use a lot in chemistry. A third scale, as I mentioned, used to be called the absolute temperature scale. It was later renamed the Kelvin temperature scale. named after a guy named Kelvin. And water boils at 373 Kelvin and freezes at 273 Kelvin. As I mentioned before, pretty much in chemistry, it is all about Kelvin in terms of calculations and using formulas. But in chemistry and in science, we oftentimes, though, will take measurements of temperature in Celsius and a lot of times has to convert it to Kelvin is a very common sort of conversion that we have to do. So I would say probably outside of chapter 2, you probably won't see too much degrees Fahrenheit popping up in any chapters and stuff like that. It definitely will be kind of confined to Celsius and Kelvin. And I would say in a lot of cases, converting from Celsius to Kelvin is probably what you would be doing. Occasionally, you do need to go back from Kelvin back to Celsius, but those are going to be your common sort of temperature units that you're going to see. So let's talk a little bit about how we kind of can convert between them. When we look at the difference between Fahrenheit, between where water, for example, boils and freezes, it's about 180-degree difference between the boiling point and the freezing point. When we look at the Celsius scale and the Kelvin scale, it's about 100-unit difference between sort of boiling and freezing of water. And that difference is what's going to basically help us with our conversions here. And let's talk about how we convert it here. So first off, if we want to convert between Kelvin and Celsius, to calculate the temperature in Kelvin, you take the temperature in Celsius and you add 273.15. And yes, at this school, they want you to do the 0.15. Outside of this school, most people roll with 273, but 273.15 is the number here that they want you to use. And like I said, you'll oftentimes see people just use 273, but get in the habit of using the 0.15 because that's what they want here. So we also will go backwards as well. So if you happen to want the temperature in Celsius and you have it in Kelvin, it's basically the opposite calculation there. You're going to take the temperature in Kelvin, you're going to subtract 273.15. So I would say probably 98% of the time, that's what you're going to be doing. And a little bit of the time, you'll be doing that. Now, to convert between Fahrenheit and Celsius, you can take the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. And if you want the temperature in Celsius, it's going to equal the temperature in Fahrenheit minus 32 divided by 1.8. And that will get you to Celsius here. As I mentioned earlier, again, probably outside of chapter 2, you're not going to probably do too much of the Fahrenheit sort of conversions. That 1.8 number is also, if you learned maybe when you're younger, a fraction sort of version of it, 9 divided by 5, then 9/5 is the same thing. You take that, you'll get 1.8, so you could use that. If you want to go, for example, from Kelvin to Fahrenheit, you have to convert it from Kelvin to Celsius and then Celsius to Fahrenheit. Or if you want to go from Fahrenheit to Kelvin, you got to go from Fahrenheit to Celsius and then Celsius to Kelvin. Clearly, as you know what I'm going to tell you, you need to know these. Yeah, so make sure that you do know these, obviously, how to do that. Any questions on that there? So let's talk a little bit about some rules here. Actually, we'll do the examples we'll talk about when we do that. So why don't we try these few examples here. So why don't you do these conversions? The temperature is 28.5 degrees Celsius. You want to convert it to Kelvin. 41 degrees Celsius, we want Fahrenheit. And the last one, 160 degrees Fahrenheit, we want Celsius. So grab a calculator, do those, and we'll talk about it here in just a second. Celsius to Kelvin. So again, to do that conversion, our temperature in Kelvin is going to equal our temperature in Celsius plus a 273.15. So putting in our numbers here, 28.5 plus 273.15. That is going to get us here about 301.65 Kelvin. Again, here we do not use the degree symbol. So what I was going to talk about a second ago, and we'll talk about right now, is this. when you are doing a temperature conversion, such as we're doing on these problems here, and that's really the only thing that you're doing, it's just kind of converting the temperature value from one scale to the next. We do follow sort of a general rule in terms of what our answer should look like. And this rule does not follow really specific significant figure rules that we'll talk about later on in this chapter. But the general rule is if you're just simply doing a temperature sort of to temperature conversion, just converting to units, is your answer should essentially look like the original number. And if we look at our original temperature number, it actually went to one decimal place. So in this particular case here, we would want to round this and not lose a number, 301.7 Kelvin, and round it to one decimal place in this case. So this is sort of a special rule for just doing temperature to temperature conversions. If your original temperature value was a whole number, you would want to take it to a whole number. If it went to two decimal places, you would want to take it to two decimal places or one decimal place like we did here. And the reason for that is really the sort of equations that we use to do the conversions. As you saw there, we have 1.80. Some people will just use 1.8. Some people will use like the fraction and stuff like that. So there's a lot of variance in terms of how you could do sort of these conversions. So that is, again, the general rule you should follow when you're doing temperature to temperature conversions. If we look at the Celsius and want Fahrenheit, our temperature in Fahrenheit is equal to 1.8. Temperature in Celsius plus a 32. That's going to be a 1.8 times a 41 plus a 32. And that's again on our calculator going to give us 105.8 degrees Fahrenheit. Once again, following that general rule, if we look at our original number here, it is a whole number, which means we would want to round this to the whole number. Because that is an 8, we would round up and we would get 106 degrees Fahrenheit. Any question on that one there? By the way, just a reminder that you are required to kind of show work. Yeah. So, make sure you are kind of showing that for sure. Just get in the habit of showing your work, and that will help you out tremendously on quizzes and exams, not just pop-up answers. Yeah. Here we're going from Fahrenheit to Celsius. So Celsius is our Fahrenheit minus 32 divided by 1.8. So popping in our number here, that's going to go 160 minus 32 divided by 1.8. 160 minus 32 divided by 1.8 here can give us a 71.111, a whole bunch of ones, degrees Celsius. Once again, looking at our original temperature value, again, we had a whole number here, so we would take this to 71 degrees Celsius. Any questions on any of those calculations there? So once again, you obviously do need to know how to do these conversions. They will not be provided for you onto how to change the temperature. And as I mentioned, pretty much your Celsius to Kelvin is a very much one you'll use the most. And Kelvin back to Celsius probably be your second most kind of use of that. All right. So as we talked about before, it's really important to understand, when you see a unit or you write a unit as to what it represents. So again, if we look at something like this, 523 Kelvin, that should be a temperature, right? So Kelvin here is a temperature. 25.36 L, which is liters. Liters is a volume. 15 meters. Meters is a length. And kilograms here is a mass. Yeah. So again, you want to make sure you understand that so you don't say something like I just filled up, 50 grams of water in the graduated cylinder instead of 50 milliliters, right? So you understand what those things mean. You don't want to say you go weighed something and it was, 60 liters or milliliters or something like that. All right. Let's talk a little bit about a couple of different sort of observations and measurements, if you will. So we do have things that are known as qualitative, and qualitative is what is known as basically general observations about a system. Qualitative typically is not a result of any type of measurement. So, you're looking at something that turns purple or, solid deforms or something like that. So qualitative is all about just sort of observations, not really measurements. When you go to Chem 1B, you do a bunch of really great experiments. Not really. You do a bunch of really great experiments that are known as qualitative analysis experiments. And in those experiments, for example, all you do is really just observation based. Did you make a solid? What color was the solid? You actually don't even measure things out when you do those type of experiments. It's so qualitative. You just go like, 20 drops seems good. That's pretty close to a milliliter. You don't have to measure out things. So qualitative is all about just your general observations. Quantitative, on the other hand, is all about measurements and numbers and values and stuff like that. So quantitative is basically when you make a measurement. Quantitatively, you would go measure out the mass of something, which means you would take it to the balance, you would put it on there, get the actual mass of that object right. If you want to measure out a exact amount of volume, you would make sure when you put it, for example, in a graduated cylinder, you get it to exactly the line that you need. Or if you're using a pipette, you draw the liquid up to the proper line. So quantitative is about measurements and values that you actually take. Qualitative, again, more just general observations about what is going on. Now, let's talk a little about what we saw earlier, which is scientific notation. And we oftentimes in chemistry use scientific notation to handle really large numbers or really small numbers. A lot of times numbers where there's a lot of zeros. And for example, as you can see there, 1 gram of hydrogen is 602.2, a lot of zeros of hydrogen atoms. And it has a mass of points, a bunch of zeros, and 166. So clearly here, if you're trying to do some calculations with those, there's probably a fairly good chance you're going to lose some zeros along the way or miscount some zeros. So to handle these, we use scientific notation. Scientific notation has a general form of n times 10 to the n. And this first one is a number between 1 and 10. So it can be 1, but it usually cannot be 10. So it's got to be a little less than 10. But you can do 1 in scientific notation. This is also a number, and this number can be either negative or positive. And what determines whether or not it's negative or positive is basically which way you need to move the decimal point to get to a number between 1 and 10. So if you had something like 4256, although there is not a decimal point actually written number, we do assume it is here. And we would need to go one place. That would get us 425, which is not a number between 1 and 10. We go one more place. That gets us 42.5, which again is not between 1 and 10. We would need to go one more place, and that gets us 4.256 times 10 to the 3 because we moved it 1, 2, and 3 places to the left. It is typically a positive exponent if the number is a large number or over 1, basically. Yeah? So if it's kind of that, it is typically a positive exponent, or you moved it to the left. If you had something like 0.00333, again, in this case, we would have to go to the right one place. That is not a number between 1 and 10. Got to go one more. That is 0.3, which is not a number between 1 and 10. We got to go one more place to the right there, and that will give us 3.33 times 10 to the minus 3. Again, here minus 3 because we went to the right to convert that. Again, you can remember if it is a small number, less than 1, it typically will have a negative exponent when you write that. So that, for example, when we saw like 10 to the minus 2 for centi in that conversion that we saw earlier today. That 10 to the minus 2 is basically 1 times 10 to the minus 2. And if you were converting it from scientific notation to, say, decimal form, what that would mean is because it's negative, it's a small number, you need to go this way 2 places and put in some zeros to fix it, and that would end up with 0.01, which again is 1 and 2 places there to the left as you go there. So if you're going from scientific notation back to decimal form, or sometimes referred to as positional notation, you're going to basically move the decimal either to the left or to the right. And if it's a negative, you should go to the left. And if it's positive, you should go to the right to make it a bigger number. Put the appropriate number of zeros in there. Any questions on that there? Oops. So that's basically what we just kind of talked about. So let's talk maybe a little bit about, more importantly, in scientific notation. Obviously, you do need to be able to properly write scientific notation. And by the way, again, because it is a number between 1 and 10, writing something like 20 times 10 to the 3, or 200 times 10 to the 3, or even 0.2 times 10 to the 3 is not correct scientific notation. So again, that first number's got to be between that. But more importantly is calculator, yes, and how to put scientific notation into your calculator. So if you have a calculator and you need to put a number in scientific notation into your calculator, in my experience, most people don't know how to do that. So let's talk about how to do that. On your calculator, you actually have sort of an exponent button, and it usually will be an EE button. It may be an EXP button. Or if you have, they're not really new calculators anymore, but if you have what I like to call like the two-tone colored calculator, kind of like a main color in the middle and like the sides are like white maybe or something like that, you may actually have a button that says 10 to the 10 times 10 to the n. And usually if you have that type of calculator, you also have like a little wheel to the right on the calculator. It looks something like that. So these are typically your exponent buttons on your particular calculators that you have. Another important button is actually the negative button. And you do want to make sure you use the negative button and not the subtract button. And most of the time, it's one of these two. That's kind of like your negative button or change the sign button, or something like that is kind of the negative button, if you will. So we'll talk about these first, and then we'll talk about what other things you got to do if you have that on your calculator, that button. So let's just say we had 1.25 times 10 to the minus 6, and we wanted to properly punch it into our calculator. What you would do is you would go 1.25. You then would hit your exponent button. So you'll hit one of these two buttons. And typically speaking, if you do that on your screen, it will look one of two ways, usually on most people's calculator. It will look like 1.25 and may actually just put an E there. Or perhaps it may look like 1.25 and maybe just pop up a couple of zeros, and you might even have like a little times 10 written there as well. And that's usually what will happen in this particular case. When you hit the actual exponent button, so when you hit this actual button here, that represents in the number the times 10 part, which means you should not use the multiplication button. Obviously, very commonly people use like shift and log. You should not be doing that either at all. All you have left really is the -6 to put in there. And what you would then do is hit the negative button, whichever negative button you have, and 6. That will then go -6 there. That will turn this into a -6. And that is the proper way to punch something into a calculator in scientific notation. You should at no point use the multiplication button to do it. You should at no point use the log button or the shift log or the second log button. And when I talk about the log button, very commonly people use it because they see this above it and think that that is how you do scientific notation. That is how you do the inverse log. And if you use that for scientific notation, down the road, you're going to be off on your calculations because your calculator thinks you're trying to do some other type of calculation. So do not use the log button when you're trying to do scientific notation. This is, again, the proper way to do it. Now, if you happen to have, again, and very commonly, they're kind of like in the two-tone colored type calculators, those buttons, you pretty much need to do the same thing, except I'll just say your calculator is programmed, I won't say wrong, but not convenient for people using it. So you actually need to put parentheses around every number that's in scientific notation, which is not a big deal. You just have to get used to kind of doing it so you do it right. So if you happen to have this buttons or those two buttons there, you would have to do open a parentheses to start with. And then you would do very similar to what we did, 1.25, and you would hit your times 10 to the end button. And what it's going to look like on the screen is you'll have a parentheses, a 1.25, it'll go times 10, and what you'll have is your cursor kind of blinking up towards the top of the 10. At this point, you could actually do the rest of it the exact same way. You just hit your negative button and 6, and what it will then turn it into is 1.25 times 10 to the minus 6. You will now have your little cursor button blinking to the right of it, and this is where the problem comes in on most people's calculators like this. You actually need to bring the little cursor guy back down from the top, and that's where the wheel comes into play. You would take your wheel, you actually would hit the right-hand side of your wheel. And when you do that, that will bring your cursor back down. And now you'll have a regular sized cursor. And now you could close your parentheses. And you'll now have, obviously, the number here properly entered. I say that because if you don't bring your cursor down on most of those calculators and you put like the parentheses up on top, you'll get an error because it's like way up on top and stuff like that. So you want to be recovered. So it's just a couple extra steps that you have to do if you have that calculator. Not a big deal. You just have to remember how to do it. But you pretty much for every single number, you do have to put the parentheses. If you actually do not put the parentheses and just punch it in without the parentheses, typically on those calculators, your calculator will break up the calculation incorrectly and kind of do the math incorrectly and get the wrong answer. So it's really important if you have that type to make sure you do the parentheses. So like I said, usually that's kind of like a two-tone calculators, typically the ones that kind of have those buttons that you need to use it. If you have a calculator that has either of these two buttons, you really don't have to be super careful. You could kind of sloppily punch it in with the exponent button, no parentheses, nothing like that. Yeah, you're good to go in most cases on those calculators. Any questions on it, put it in there. All right, so let's try it, make sure. Let's just do 1.25 times 10 to the minus 6 divided by 3.2 times 10. Let's do 23. Let's see what you get. And let's do 3.4 times 10 to the 6 times 1.2 times 10 to the minus 11 and see what you get there. So punch those in your calculator properly with scientific notation and see what you come up with. Okay, so let's take a look. So again, if I was to punch the first one in here, I would punch it in my calculator, so 1.25. Again, I would hit my exponent button. I would hit my negative button and 6. I would then hit my divide button, 3.2. Once again, exponent button and 23, and obviously my equals button. Again, if you have the other calculator, parenthesis up it, both of those numbers. So 1.25. Actually punch it in better, 1.25 exponent minus 6 divided by 3.2 to the 23. That's going to give me on my calculator on my screen here, should get something like 3.90625. On my screen, I have an E minus 30. On some people's screens, you may have a times 10 to the minus 30 as well towards the end of it. So first off, we want to round this, and we'll talk about the rules, but this would get rounded to 3.9. Now, it's really important and very common. Sometimes people forget the back part here. And just like when we punch in the E, it represents the times 10. When your calculator gives you the E in an answer, that is the times 10 part of the number that you want to write. And this would be minus 30. You should always, when you're writing the answer, use times 10 and not E. So you should not write 3.9 E minus 9. So you should write 3.9 times 10 to the minus 9. The E is used in calculators. It's used in things like Excel and stuff like that to do scientific notation. But when you are writing scientific notation or given it as an answer, you really should not use the E for scientific notation. You should use the times 10 part. You do not want to forget the right-hand side there because, again, it's very common. People will look at their calculator and just write the front part of the number and forget the back part of the number. So you want to make sure you don't do that. By the way, when we do write a number that's in scientific notation, all of the numbers that come before the times 10 part are significant. So these are significant numbers. So whenever you see a number that's written in scientific notation, it is assumed that all the numbers that come before the times 10 part are significant numbers. We're going to talk about significant numbers, obviously, in this chapter. So when we look at the original number here, that has 3 significant figures because there are 3 numbers before the times 10 part. This guy would have 2 significant figures because there are 2 numbers before that. And as we'll talk about, when you actually divide or multiply, your answer should have the same as the one with the least number of significant figures. So in this case, that's why we actually rounded it to 2 significant figures, or 3.9 in this particular case. We will talk about the rules obviously coming up here shortly. Any questions on how to punch that in there? Now, if you find yourself with like this number correct, but this number is incorrect, it is usually how you're punching it in, like you're adding some extra steps there, like the multiplication button or something like that, that you should not be doing. All right, so if we're gonna do the bottom, same deal. We're gonna go 3.4. Gonna hit our exponent button. This is a positive exponent, so we're just gonna go 6, because we don't need a negative. We're gonna hit our multiplication, 1.2, once again, exponent button, and negative button, and 11, and equals. And if we do that there, you will end up on your calculator here. In this particular case, I end up with 0.1234408 on the screen. So this also brings up a really good point. Your calculator may not give you your answer in scientific notation unless you have a program to do so. You don't necessarily have to give an answer in scientific notation unless you're asked to do so. Sometimes, though, the only way to sort of give the correct answer in terms of proper number of significant figures is to actually write it in scientific notation. So sometimes you kind of have to do it. So in this case here, both of these have 2 significant figures. So our answer actually should have 2 significant figures. So you could give it one of 2 ways, 0.00004, and because this is an 8, we would round up. You could also turn this into scientific notation again, 1, 2, 3, 4, 5 places, 4.1 times 10 to the minus 5, bless you. So you could do either one in this case. Any questions on that there? So again, I would say you definitely need to know how to write things in scientific notation properly. You need to be able to go from scientific notation to decimal form properly. But probably more and more important is you need to know how to punch it in your calculator correctly and use it that way. Because I would say most of the time you probably may be given a number that's in scientific notation, need to punch it in and get the right answer. So hopefully you now know how to do that. If you still are not sure, at some point, come see me with your calculator. We'll find your exponent button and show you how to punch it in, okay? All right. All right. All right, so why don't you take a second here for each of these, write them in proper science. Okay, so let's take a look. So again here, we need to actually go to the left. So 1 and 2 places to the left will give us a number between 1 and 10. That'll give us 5.68762 times 10 to the 2. This is a big number, so we went to the left there. We're going to go positive exponent. There is a reason we actually keep all those numbers, and the reason, as we'll talk about in this chapter, is they are all significant, so we should not lose any significant figures as you go from like decimal form to scientific notation or scientific notation back to decimal, and we'll talk about how you can identify shortly, but that is the reason we're keeping all those numbers. Here, we would need to go 1, 2, 3, 4, 5, and 6 places if I counted right. That will give us 7.72 times 10. This would be minus 6 as we went to the right there, and it's a small number. We need the negative for the exponent. Here, there is not a decimal point written, so it's assumed that it is at the end. So we'll go 1, 2, 3, and 4 places. 1.25 times 10 to the fourth. Here we actually don't keep the zeros, as we'll talk about, because they are not a problem. And lastly here, one place. 1.35 times 10 to the minus 1. Any questions on how to write those? All right. So same idea here. We'll go from the end here. 1, 2, 3, 4, 5. 4.25 times 10 to the fifth meters. And here we'll need to go 1, 2, 3, 4, 5, 6, and 7. Gives us 8 times 10 to the minus 7 grams in this case. All right, so then let's talk about measurements and uncertainty in measurements. So whenever we take any type of measurement, there is some degree of uncertainty. There's really some degree of estimation, or not really guessing, but some type of estimation, hopefully. The degree to which you have to sort of estimate is based on the equipment that you're using. So whenever you make any type of measurement, for example, in the chemistry lab, you should always look at the piece of equipment you're using. You do need to figure out usually how far you could take the actual reading to. So usually measuring equipment has some type of scale that's written on it. You need to look at the scale and sort of figure out how far you should actually take the reading to. So for example here, if we took, I'll go 2, I'll learn to count. We'll go 1, how's that? And 2. And we'll do that, kind of connect it. Okay, so we'll just say this is a ruler and these are centimeters, for example. And let's just say we have an arrow popped out there somewhere. And we wanted to measure this arrow. So typically when you look at a measuring device, such as a ruler or any glassware or anything like that, like I said, there's usually markings. And there's usually kind of two types of markings that you would see. There's typically a large marking. And large markings are typically the ones that actually have numbers on them. So these would be kind of considered your large markings. And there's usually small markings, which are basically all the markings that fall between the numbers, basically. All these guys here are basically our small markings that usually do not have numbers associated with them in most cases. So the first thing we could clearly see on this scale is, in terms of the large markings, there's a 1 and a 2. So the difference between 1 and 2 is each large marking represents 1 centimeter in this case, right? Now, what we want to then do is count up how many of the small markings there are between those two. So it's really important you also count correctly. So when you're counting the small markings, you actually start past the last large marking. So when we're starting to count, we would actually start counting here as 1, 2, 3, 4, 5, 6, 7, 8, 9, and you end on the next large marking. So that would be 10 markings between the two large markings. So that means that each of the small markings represents how much? Each of the small ones represents 0.1 centimeters. Yeah, You could get that by dividing this by 10, yeah? So if you divide that by 10, you get 0.1. That means that this first small marking is basically 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 10. First off, any questions on that there? Okay. So when we take a measurement, there should always be numbers that pretty much, no matter who takes a look at it, everybody should agree upon. So everybody, hopefully, if they look at this, should agree that my arrow is at least 1.5. So it is definitely past the 1.5 marking. So you should record that 1.5. Those 1.5 is what is considered all the certain numbers. So these are all the numbers that no matter who takes a peek at it, everybody definitely should agree upon. Now, the problem though with this measurement is my arrow is not exactly at 1.5. It is really not exactly at 1.6. It is somewhere between the two. And it's somewhere in this ballpark here, right? Now, this is where the estimation comes into play, the uncertainty in this measurement. I may look at that, and even though I could not draw a straight line-ish, I may think that is just a little shy of halfway between the two, right? And we could think halfway between the two would be a 5, right? If you kind of think about it, right? So maybe I say this is a 4, and I go centimeters, right? And I do want to include the units here. This number that I call the 4 is what is referred to as the first uncertain number. And really where the uncertainty in this measurement basically lies. Now, somebody else may look at it and go, I think it's more like 5. It's like halfway-ish there between it. Or maybe some people may think it's a little less. And that's again where sort of that uncertainty lies. We can look at this, and when we take a measurement, we always want to record all that first uncertain number. And when you do that, that is basically what significant figures are, which would mean this particular measurement would have how many significant figures? It would have 3 significant figures in this case, with the uncertain number being the 4 in this measurement. And typically speaking, what we're really saying in this case is, I think it's 1.54, but maybe it's like 1.55, maybe it's a little less, maybe it's like 1.53. So a lot of times plus or minus 1 of that last number is sort of where the uncertainty lies, because you hopefully should be able to kind of measure it pretty good. Any questions on that there? Now, it does depend on what you're using. So, for example, if you had a really badly drawn graduated cylinder such as this here, I'll go here. I'll barely squeeze it in there. Not bad. All right, we'll go 10 and 20 there, and we'll go milliliters. And let's say we put in here, for example, a liquid. And by the way, when we do measure a liquid, typically the liquid in a glass container will curve, not maybe this dramatic, but this will make a meniscus. And we typically will read, in most cases, especially when it's a U form like this, from the bottom of the meniscus is typically where we want to read. The reason for that is something we'll talk about in a later chapter. When a liquid gets in contact with the walls of like a glass container, the attraction between the liquid and the glass is actually stronger than the liquid in itself. So what happens, capillary action, those guys in contact start rising up the side of the actual container, and it makes this meniscus. The reason we read the middle is because in the middle is not touching the sides, right? And that's actually where the volume would be if that interaction wasn't happening. So that's actually where the volume actually would be. 99 times out of 100, your meniscus will look like that. It can actually go the opposite way occasionally. It can't kind of go this way. In this case, we would actually read the top of the meniscus if it went that way. Mercury, for example, is something that will do that. And since they've taken mercury out of labs and stuff, you don't probably come across it all that much, but mercury actually goes that way. It's the same idea. The difference, though, is why it kind of goes that way on that particular one is the attraction between mercury in itself is actually stronger than the liquid in the container. So it actually comes in on itself and kind of goes downwards and makes that kind of reverse one. But most of the time, this is what your meniscus is sort of going to look like. It is sometimes easier to see in certain glass containers, bigger sort of containers. Sometimes it's harder to see it. So when you do take a reading, you do want to do that. But coming back to this, again, if we look at our large numbers here, we have a 10 and a 20. So each of our large numbers, the difference there is 10 milliliters in this case. When we look at our small markings, again, starting to count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, we have 10 markings, so 10 divided by 10 is, each of them equals 1 milliliter in this case. Again, if you divide that by 10, you could get down to there. That means that this guy would be 11, 12, 13, 14, 15, 16, 17, 18, 19. And if we read from the bottom of the meniscus here, ish, in my badly drawn one, just kind of go this way. We're right about there. So once again, we could record in this case, it is definitely 16, which is a certain number. Once again here, we are not exactly at 16, not exactly at 17. In this case, we maybe are somewhere halfway between the two. So this again would be our certain numbers. We record 0.5 milliliters. This would be our first uncertain number. And that again is going to give us 3 significant figures in this particular case. Now, in this particular case, we could only go to the first decimal place. In this case, we could actually go to the second decimal place. So it does depend on the scale that you're looking at. Typically speaking, you could usually go one more place to the right of the smallest marking. So the smallest marking here is a whole number. We could go one more place to the right, which is the first decimal place. Smallest marking here was the first decimal place. We could go one more place to the right, which would be the second decimal place. So in most cases, you could go usually one more place to the right of the smallest marking. Any questions on that there? All right, we will lay it up there for now.